Okay, good morning, everyone.
Good morning, sir.
Since we are in the last week of classes, let's once again start with the questions that you may have. And most importantly, what we have to get done is to understand how NOESY and other 3D experiments would help you get the structure of a protein. That's the overall exercise. Unlike the other parts of the course where we were extremely quantitative, for these classes, I'm going to be quite qualitative, except for the discussion of the Solomon's equation. Solomon's equation lend hand to the block equations, where block equations, we looked at relaxation that happens across the transverse and longitudinal magnetization. Here, we would focus ourselves only with the longitudinal magnetization and ask, when you perturb it away from equilibrium, what happens? Basically, you should put the Solomon's equation and block equation together to solve the entirety. But since we are only looking at longitudinal magnetization for the NOESY, the set of IZ, SZ, and 2IZ, SZ are enough to understand what's going on. With that, I would like to say that there were mistakes from the Friday lecture where the terminology had a problem, which we will correct right now. Let's get started. Do you have any questions? Is there a lack of understanding somewhere?
For 2IZ, still what I did just for what I did at IZ, just the plus sign gets minus sign.
I will try to do this again so that it's a little more clearer. Even I was thinking how to present it. I'll try to tell you. Your question is, how is 2IZ, SZ represented as N1, N2, N3, and N4? How do the plus and minus signs come? Even I was thinking about it today, how to make you guys understand that better. I'll try to do that today. Okay? And today, in order to minimize any mistakes that I might end up doing, let me exactly repeat what Keeler had done. Okay. So let's go ahead and once again draw the 4 different energy levels. So we are talking about 2-spin system, homonuclear INS. You can imagine them to be 2 protons. Quite commonly, nuclear Overhauser effect is done between protons. Okay. So let's take that for a discussion. And what we said here is that it'll have 4 energy levels: alpha, 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 beta, beta, alpha, beta, beta. And I think Keeler likes to give notations as 1, 2, 3, and 4. And then similarly, the transition probabilities, he's calling this as omega S. Once again, this is where I made a mistake. Yes, omega S1. I didn't make a mistake. I think in the final conversion, I made a mistake. Where this is the S transition happening with index 1, and the index 2 for the same one will be here, WS of 2, where it's between the transition of beta alpha to beta beta, where only the second spin changes. And this is WI of 2, where the I spin changes with the S spin being in beta. And then we also had other transitions, which are double quantum and 0 quantum. Yeah. And then we took an example and we wrote what is d alpha alpha over dt. As I said, in order to minimize mistakes, let me follow what Keeler does. dn1 over dt would be given by minus wi1 minus ws1 minus w2. So therefore, I took the entire minus an outside times n1. Yeah. Plus wi1 w3, sorry, n3 plus ws1 n2 plus w2 n4. This is what we wrote. And similarly, if you guys calmly sit and write dn2 over dt, dn3 over dt, and dn4 over dt, following similar, this is like, these are like kinetic rate equations, you would be able to write them, right? With that being the case, the next step that was done is to write the operators in terms of these populations. We take inspiration from the spin half system, where you have alpha and beta, and we said mz, which is like iz, is nothing but n alpha minus n beta. You guys remember this, which is population in alpha minus population in beta. We are going to do the same thing here, meaning that let us take IZ for instance. IZ would be determined when their populations, when its spin state changes from alpha to beta. Correct? Yes. So therefore, this is one transition that involves I. So are you guys ready to accept it's going to be N1 minus N3? Similarly, you also have I spin flipping here. So it's also going to be plus N2 minus N4. People who understood this, please raise your hand. Good. So with that being the case, SZ is going to have a similar argument. S flips between these two. So therefore, since N1 is the lower state, you'll say N1 minus N2, because these two are the states that you're interacting. Similarly, these two are the states plus N3 minus N4, right? And the two IZSE, just take the IZ1. N1 and N3, the spin state of S is alpha. So kind of multiplying into the half or whatever, plus half. Let's say plus 1, because you don't have to worry about the units here currently. On the other hand, N2 and N4 have S spin in the beta state. Okay, if you operate the SZ on them, you are going to get a minus sign there. So therefore, that will end up flipping only the N2 and N4 in sign. Okay, so that's how you get it, right? And you need to have, we have 4 variables. You can rewrite them into 4 other variables across various unique combinations. E is going to be sum of populations, which will be set to 1. Okay? So now what you can also do, what we wanted to understand is the rate of change of longitudinal magnetization, diz over dt, which is going to be dn1 over dt minus dn3 over dt plus dn2 over dt minus dn4 over dt. Right? With this being the case, you also just saw how one can end up writing each one of them, and therefore you would be able to push them into this, right? Not going to spend writing all these terms because each one has like 6 terms. 6 times 4 is going to be 24 terms. If you put all the 24 terms together, I'm just going to write what you finally end up getting. Let me write it and speak because I might end up making a mistake. So this is what should end up coming. Okay. So once again, if you put all these set of equations together, you have multiple variables here. You end up substituting here. You end up using all these identities. You will end up getting diz over dt as a function of iz separately, nz separately, and 2 izsz. Okay. Sorry? Okay. Basically, my indices are wrong is your point. Yeah? Is that better now? Yeah. Okay, so this is what you will end up getting. If you might remember the argument we made for a spin half system, you should introduce minus iz of 0. You should also introduce minus an iz of 0 in order to establish the thermal equilibrium. But remember, thermal equilibrium is a constant, isn't it? Right? Anyway, so we will continue to do this. So similarly, if I have to end up writing dSZ over dt, that's going to be equal to minus ws1 plus ws2 plus w2 minus w0 sz minus w2 minus w0 iz minus ws1 minus ws2 to izsz. Okay? One can write the same thing for 2 izsz as well. But for the sake of this course, let's keep things simple. We'll say that omega S1 equal, sorry, WS1 equal to WS2, WI1 equal to WI2. Okay, so therefore what is going to happen? For this assumption, these things will go to 0. So basically what can one write is diz over dt will be given by minus omega W1, Wi1, Wi2 plus W2 plus W0 Iz minus W2 minus W0 Sz. Similarly, dsc over dt will be given by minus ws1 plus ws2 plus w2 plus w0 sz minus w2 minus w0 iz. I've just removed the 2 iz term, saying that for all practical purposes, let's assume the transition probabilities where S transitions happen, the frequencies are the same irrespective of the state of the I spin. We have invoked the same assumption for Wi as well, similar to Ws. Okay, for small molecules, a very good assumption. These things start to change as you start increasing the size as well. One of the most important things that you're able to read out of this is that Iz relaxes due to itself. It depends upon wherever it was. Remember, this has to be also updated a bit. How should it be updated? This should be Iz minus Iz of 0. What is Iz of 0? The equilibrium magnetization of I itself. Okay, and similarly, Sz should be Sz minus Sc of 0. That's equilibrium magnetization of Sc itself. You might always ask, why are we not writing Iz minus Iz of 0 here? Remember, that's a constant. D by dt of the constant is going to be 0. So all that you need is these, right? So this way, what can one do is that the d by dt of Iz can also be written in a matrix form, okay, where this first part will be written as Ri because it's only depending upon its own magnetization changes are happening, right? Similarly is this case where this will be R of S. I'll come to these terms in a moment. On the other hand, we'll try to understand what these two terms are. So that will be represented as sigma Is. This will be sigma Si. So what could one write is that something like Ri minus sigma Is minus sigma Si minus Rs Iz minus Iz0 Sc minus Sc0. Okay. So what are we learning from here is an important lesson. One can always argue what's going on here versus what is going on here. This term is called self-relaxation. What is self-relaxation? Depending upon how far you are from equilibrium, the relaxation will happen by itself. An example, if I have to take, if your steady state or equilibrium is your room at ICER, if you're outside your room, right now you're in a classroom, how quickly you go back depends upon how far you're from your room. On the other hand, you also have influence that comes from its dipolarly coupled spin, which is the Sz spin. How far is your room, your friend also away from room matters here. Let's say you are in your room and your friend is away, you're still perturbed actually. Maybe you want to talk with your friend. That's the entire thing this whole story is trying to say. The recovery of the I spin, the longitudinal magnetization recovery of I spin, not just depends upon its own deviation from equilibrium, it also depends upon the deviation of its dipolarly coupled spin from equilibrium. Okay? The one that makes it comes back by itself is called a self-relaxation. The one that makes it come back due to its dipolarly coupled spin is called cross-relaxation. Okay, this cross-relaxation term is the one which allows for generation of Sz from Iz itself. let's go back to think what was the NOESY pulse program. We drew the pulse program as something like this: 90x, 90x, 90x. This is T1 evolution. This was mixing time. Okay. There's one more thing that comes up here, which is like a gradient that is applied during the mixing time. Since I've not taught you what is a gradient, I'll just give you an idea. Kills anything that is along X or Y. It kills anything that's transverse. Because you're applying only one gradient right now, you can imagine gradient as a magnetic field that's applied along the z-axis. If you apply a magnetic field along the z-axis, which changes as a function of z, it's going to kill anything that's transverse. Okay, so for now, instead of going to the complications of what does a gradient do, you can assume that the gradient ends up killing that's anything xy. Okay, so let's follow through this pulse program. You start with IZ. You apply a 90x, it's going to be minus IY. For T1, it's going to be IY cos omega I T1 plus IX sine omega I T1. Right? Yeah. Now, if you apply the next 90-degree pulse, once again along X, what is going to happen? You're going to have minus IZ, minus IY go to minus IZ cos omega I T1 plus IX sine omega I T1, right? When you end up in the mixing time, nothing is applied. Okay, you might ask, why are we not invoking the scalar coupling between I and S? You can always invoke, more terms will come. They'll just split. I don't want to write it because it's just going to complicate more terms, but you can imagine that if you have a chemical shift, it's going to just split by that coupling. We have done this enough right now. That's why I'm not invoking scalar coupling between I and S. Anything that's dipolarly coupled need not be scalarly coupled as well. We will take some examples as we go forward. Only if they are within 3 bonds, they are scalarly and dipolarly coupled. But there are ones that could be close in space, but are too far in chemical bonds, and therefore they won't have scalar coupling. We are trying to look for such examples right now.
Scalar coupling, so it only transfers to the bond.
This is through space. Whatever we are trying to talk right now, this is through space. These are two dipoles, magnetic dipoles. You can imagine these two are two small magnets suspended in the Earth's field. They will be oriented by the Earth's field, but depending upon how close they are, they will also exert a force on each other to orient themselves.
Scalar coupling interaction happens through
bond. Scalar coupling happens through bond. This happens through space. There are two magnets that are just close versus two magnets that are connected through the sigma bond. That's why that's called scalar coupling. Yes.
So what is the difference between that small omega and big omega?
What is the difference?
The small omega and the big omega,
The only difference is that I'm not being consistent. Thank you for pointing it out. Thank you. This is the problem when you use multiple terminologies same time. So I kind of confuse my own brain. Thanks for pointing it out. Yeah, so this is through space. So I'm not writing the scalar coupling component here. So now in the tau m period, no pulses are applied. Z is longitudinal magnetization. X is going to experience relaxation, transverse relaxation. But most importantly, the application of the gradient is just going to kill anything transverse. So you're only going to have minus IZ cos omega I T1 remaining there. Okay? Now is where the magic happens. Let's assume that the gradient is applied initially itself, which kills everything. You have the tau mix that is being present. Right? Now go back to whatever we started with. The rate of change of I magnetization would end up creating S magnetization due to this cross relaxation term. What do I mean by this? Some part of this IZ, let's say alpha equivalent of this IZ, is going to get converted to SZ. Once again, what we are trying to say, the cross relaxation, you're talking about rate of change of IZ. It's just not going to be relaxing through its own self-relaxation. It also depends upon the cross relaxation term, which will result in the other term coming up. Do you see the SZ term will come up? Right? Take the matrix product, rate of change of I will result in some Z coming up, provided sigma IS is non-zero. Let me repeat again. If I and S are not dipolarly coupled, where sigma IS is 0, then the alpha will go to 0. Alpha is just a random number that I took. Alpha will be dependent upon how strong W2 minus W0 is. If W2 minus W0 is very high, there's a lot of transfer that will happen. If W2 equal to W0, no transfer happens. So there are situations where when the transition probability of double quantum and zero quantum match, you'll not get any NOESY peaks, although two spins are close in space. So there are some parts of this experiment which is blind to some molecular weight. I'll come to that later. But if we agree that W2 is not equal to W0, that means sigma IS is non-zero. If sigma IS is non-zero, and if IZ is not in its equilibrium, then this IZ will result in some transfer to SZ. Okay, that's essentially what happens in this NOESY experiment. This is why one cannot use the entire density matrix of formalism to understand this, because one has to understand there is something called a cross relaxation term that exists. Okay. Now, what did I say? This alpha depends upon W2 minus W0, which is sigma IS, also depends upon 1 over R power 6. I'm just going to leave it qualitative here, because the more I go into it, then we have to understand other relaxation stuff, which I've said I'll keep off from this entire course because of want of time. Okay. So what does this mean? This means that as you go farther and farther, you will not be able to see the cross peak. And remember, it's also sensitive to 1 over R power 6. This is why conventionally, if the distance is greater than 5 angstroms, nowadays with higher sensitive instruments, 6 to 7 angstroms can be captured. But for something like 5 angstroms, you'll get no cross peak. Okay, let me correct it. 6 to 7 angstroms in, say, 700 megahertz with cold probe, cryo probe. Okay, this can still be seen. But conventionally, these were all done in the 80s, where the sensitivity of instruments were not high. So people tend to say around 5 angstroms is the NOESY cutoff. What is this cutoff? Anything beyond 5 angstroms, the 1 over R power 6 is so small that you will not end up seeing it. Right? And therefore, what is also going to happen from 2.5 angstroms to 3.3 angstroms, the NOESY peak will die very quickly because it's a 1 over R power 6. Right? Why did I choose 2.5 angstroms? That's kind of closest where two atoms can be together. There's something called van der Waals distance. You cannot be on top of each other for sure. Okay, you cannot be also kissing each other. So there should be some distance between them. Okay, there are other non-bonding interactions that exist that limits the distance between two atoms to a certain number. So NMR is very sensitive at low distances, but not many things are very low distances. But we'll see some examples as we go forward. Okay, but we still did not finish this experiment. The moment you are able to see this, what you are able to appreciate, if you end up applying the final 90-degree pulse along X, you realize that this will become SY, and that will be detectable, right? When you're detecting SY, remember you're going to get omega S and T2, right? Therefore, that's going to result in a cross peak of omega I, comma omega S, only if those two spins are dipolarly coupled. That means they're close in space with respect to each other. So the NOESY experiment is going to be one where when you have the 2D experiment, let's say this is for the I spin and this is for the S spin, then you're going to get a cross peak only if I and S are close to each other. What do you mean by close? Less than 5 angstroms of each other. right? How does a cross peak come? Cross peak comes only if there is a transfer, and the transfer will happen only if they are close in space. The transfer will happen only if they are close in space, and the probability of transition for the double quantum and the zero quantum do not match each other. Yet again, due to reasons of not discussing relaxation, the W2 and W0 kind of become equal when the molecular weight of the system goes very close to 1500 Dalton. Okay? Basically, what happens is that you have a transition like this. Let's call it NOE transfer. NOE transfer starts negative and goes to zero and kind of saturates. So there is a region. So these are small molecules. These are large molecules. And this is somewhere at 1.5 kilodalton. So that is a region where even if you have two protons that are close, you will not see a NOESY peak, cross peak. That's due to other reasons. But predominantly, so what am I trying to say as negative is that when you end up running the NOESY 2D, for small molecules, if the diagonal peak is positive, cross peak will be negative. On the other hand, for large molecules, if you end up running the NOESY, the diagonal peak is positive, cross peak will also be positive. That's all the sign of the NOESY component is saying. Okay? So what am I trying to make you guys understand? I hope from the Solomon's equations, you're able to understand how the recovery of longitudinal magnetization not just depends upon its own magnetization and how far it is from equilibrium, it also depends upon its closely dipolarly coupled spin and how far it is away from its equilibrium. Make sense? Let's just take a simple example here. Not the best of examples, but let's try to take it so that we understand. Let's take our favorite molecule, ethanol. Okay? This will be a triplet at 1 ppm, this will be a quartet, and this will be a broad, this thing. So let's say 1 ppm, 3 ppm is what you have. Remember, these two protons not just are scalarly coupled, but they'll also be dipolarly coupled, right? Now, the interesting thing here is that what are we trying to do? Somehow, let's say we are able to invert the methyl proton only. We can apply something called a selective pulse. We can do a 1D NOESY. What's a 1D NOESY? Instead of getting a 2D NOESY, what's a 2D NOESY? You have T1 and T2. Instead of evaluating this at all, just make life simple. Just don't have the T1, just apply both pulses together. Therefore, it will be a 180-degree pulse on the methyl peak, right? Interestingly, what will happen for this experiment, if you invert the methyl peak, if you let the tau mix happen and apply a 90-degree pulse. So what do I mean? I mean, draw the pulse program. Let's do a 180-degree pulse on methyl group only, then tau mix and a 90-degree pulse. When you end up acquiring, in theory, what you should have gotten, you would have only gotten a negative peak with respect to methyl, correct? Since the methylene group, I'm not drawing the chemical shifts properly. Let me do it properly. This is how it will be, isn't it? So if you end up inverting the methyl peak at 1 ppm, you will nicely get a NOESY cross peak at 3 ppm, indicating that the methyl peak and the methylene peak are close in distance. Does that make sense? This is how conventionally NOESY experiment was started. People were doing 1D NOESY experiments where if you have many resonances, you hit one by one resonance and ask which other resonances come. Whichever resonance comes indicates that it's close in space. Okay, the only problem with this is that when you go to proteins, you have too many peaks. If you have to do this in 1D fashion, you will never finish. Therefore, the 2D experiment comes to the rescue where you hit everything together. You're going to get cross peaks all over depending upon which is close to space and which is not. That makes sense? That's the power of the NOESY experiment. We pause here and ask if you guys have any questions.
Basically,
Sir, can you go a bit up? Yes, sir. So you have written that sigma is and sigma si separately. Is there a difference between those?
No,
Or
I think these are just complementary, meaning that this would be a symmetric metric. So the extent to which I spin helps S spin recover will be the same extent to which the S spin will help I spin to recover. So these are symmetric, equal and opposite terms. So basically in a 2D NOESY experiment, if you end up collecting data, the information potentially, if you forget transverse relaxation happening, the information that you extract from this cross peak will be identical to the information that you extract from this cross peak. That's about it.
yes.
Okay. Yeah. So that's the impact of a 2D NOESY experiment. Any other questions? Okay. Let's rewind back and try to understand what did we do for the last few classes. Our purpose was to say, how does NMR help in biomolecular structure determination? We took protein as an example. The first part we discussed through bond experiments. We said that 2D experiments are important, 3D is also important. And the 2D, we said the nitrogen proton HSQC and the carbon proton HSQC are important experiments to get kind of molecular fingerprints, especially the nitrogen proton forms a molecular fingerprint. But we said in order to get sequence-specific assignment, we have to build it upon the 3-dimensional NMR experiments where we did see about the 3D HNCO and then the 3D HNCACO, which potentially could good sequential assignments. At the same time, one of them raised the point that maybe you have resonance overlap in C prime or in nitrogen. Then we said, yes, that's correct. Then therefore we go for HNCA, which connects the H amide proton, amide nitrogen to I and I-1 C alpha. We also said we can also measure HNCOCA, which both put together will give sequential assignments. In the unfortunate case where C prime and C alpha have overlap, we had other experiments, 3D HNCACB, which will correlate the C alpha, C beta to the amide proton and nitrogen for I and I-1, right? And then that can still be clubbed with 3D CBCA CONH experiment, which starts from the HAHB and jumps to the amide nitrogen and proton, right? If that also doesn't make you happy, what could also acquire the 3D HBHA which is an experiment that correlates the protons to the protons. So you can keep on building up more and more experiments to get as many chemical shifts. The first set of experiments should give you HN, nitrogen, and C prime, of course, of I-1. Actually, I and I-1, because you are able to do the sequential assignments through these two experiments. Correct? In the case that you are not able to bridge the gap completely, this experiment, in addition to giving all this, will also give you C alpha. Right? This experiment, in addition to giving C alpha, will also add C beta to your repertoire. Right? This experiment will add HA and HB also. So this way, you would be able to take all these chemical shifts and be able to get sequential assignments across the protein. So these are through bond experiments. But the crucial aspect is not just to get the assignment for the HSQC, but also to look at how does a tertiary structure look, right? So that one could get through space experiments. And that, yes.
sir, how can we identify which amino acid that particular peak corresponding to? How do you identify whether I is a valine or I is a alanine?
Okay, so maybe I didn't make it clear. To start with, you should know the primary sequence of the protein you're working with. Okay, NMR cannot work if you do not know the primary sequence. Okay, you have to know the primary sequence to start with. You cannot identify or sequence proteins using NMR. You potentially could, but that's going to be a arduous task and can be done better by other techniques, not by NMR. For NMR, you got to be 100% sure about your primary sequence. This is why when you prepare your proteins, you have to purify it so that there are no other contaminants that are being present. Interestingly, if you start with the primary sequence while you're doing this assignment, if something does not fall in place, it could potentially imply your primary sequence is wrong, or there are some post-translational modifications that exist in your protein. For people who understand protein biophysics, post-translational modifications mean amino acids that will undergo further chemical modifications after the system has been generated by the bacteria or the cell. Okay, phosphorylation is a very common post-translational modification that has very important functions in the cell. I hope this makes sense to get an idea how do you get sequential assignment. But you must start with a primary sequence that you're 100% sure. And how are you sure about the primary sequence? It goes back to the fact that the DNA plasmid that you end up using to do the recombinant DNA technology to make your protein will decide your protein sequence. Right? So generally, how do people study proteins is that they would have already known from biology some protein is important. The moment biologists figure out some protein is important, one of the first things to figure out is what is the primary sequence of the protein, which is generally decided by the DNA coding sequence. The moment you know the DNA sequence, you know which codon transcribes to which mRNA translates to which amino acid. The moment you know this sequence, you know the protein that is of interest, you go to the gene region of the protein, then you'll be able to know the protein sequence. Then generally what people do, you also have the ability to create a plasmid to code whichever protein you want. Then you take this plasmid, give it to a bacterial cell, and then feed the bacterial cell 13C and 15N enriched chemicals. For instance, we'll feed it 13C labeled glucose and 15N labeled ammonium chloride, salt. So this way, what will happen? The protein that's being synthesized will be labeled with 13C and 15N, 100% label or 99% label. So this way, every atom is NMR active except for the carbonyl oxygen, right? So I hope this makes, and so therefore you will be quite confident in the primary sequence that you're starting with. Unless you have trouble where there is too much chemical shift, degeneracy and overlap, then you need higher dimensional NMR experiments to get further information to resolve the degeneracy. So now the last part is what we discussed today is the NOESY experiment. Remember the 2D NOESY, because of the fact that you have too many protons, the 2D NOESY is also not a very smart experiment to do, right? So generally what people end up doing is stitching multiple experiments together. For instance, 90X, T1 labeling, tau mix, and then yes, that's right. Somebody murmured. What is this? What am I clubbing this experiment with? Louder? That's right. Yeah. So this way, what you end up getting is that, for instance, there's a remote proton somewhere, and then you end up jumping. Let's say this is 1H and this is 15N. So let's say that this is somewhere in a tertiary space. Let's not worry about it's through bond or not. Let's say these two are within 5 angstroms. If you're able to see this specific experiment, in T1, the omega H of the remote proton will be labeled, let's say omega H remote, which gets transferred to, let's say omega Hn, which gets transferred to omega N. So basically, this will be the T2 dimension. This will be the T3 dimension. So this way, what one could do is that the proton-proton NOESY, which is going to be overlapped significantly, can further be resolved with a nitrogen chemical shift. Right? So for instance, let's say you have a 2D NOESY, which has too many peaks. This is a diagonal and you have too many peaks. You can't see what's going on here. You can resolve it to the third dimension, perpendicular to the plane of the paper I just drew, with the nitrogen chemical shifts. How do you end up getting? Is that the NOESY experiment jumps from one to the other. Let's say this is the I spin, you jump to the S spin, right? And therefore you get a cross peak. But now if the S spin can be correlated to its own nitrogen, it gets additional resolution in the third dimension. Makes sense? You could always ask, why are we doing a NOESY HSQC? Why can't we do a HSQC NOESY? We need to do the HSQC first and do the NOESY jump. You can do both. But due to certain reasons of water suppression, the NOESY HSQC is a better experiment than the HSQC NOESY. Let's keep that away for the time being. You can always do a NOESY HMQC also. Okay? So there are multiple experiments now you can start putting together. The other modules that I've not discussed with you guys is called the total correlation spectroscopy. Okay, it's called the TOCSY, which once again works through bonds. It's similar to the COSY experiment. What did the COSY experiment do? COSY experiment transferred proton-proton correlation within 3 bonds. Right? The TOCSY experiment can transfer beyond 3 bonds, like 4 bonds and 5 bonds. So one can end up doing a COSY followed by HSQC, TOCSY followed by HSQC, COSY followed by a NOESY, NOESY followed by a COSY. You have n number of combinations that allow you to actually do whatever you want to do, which is where the review that I had shared earlier was taking you to. I don't expect you guys to read the review for the exam, but this is for the people who are really interested to learn how does NMR work to get the 3-dimensional experiments. So this is giving you an idea how multiple things can be put together, right? So basically, this is where they start with. I ended with this. So you start with the through bond experiments. You start with the through bond experiments, and then the NOESY resolved by the carbon and nitrogen gives you additional resolution to get more distances. Okay, why are we so obsessed about distances? If we understand that, this will get better. For 2 atoms, how many parameters do you need to define their structure? Very good. What is that? Distance between them. Right? When you have 3 atoms, how many parameters do you need to define them?
3.
What are the 3?
2 distances and 1 angle.
Excellent. 2 distances and 1 angle. Right? Let me complicate this a little further. When you have 4 atoms, what else do you need? Atoms 2. I'll write parameters, okay? You need only 1 parameter to define 2 atoms, the distance. When you have 3, you need 3 parameters. Now you're going to 4 atoms, right? What is that? What else do you need?
2 distances and 1 more angle.
1 more angle. Excellent. Excellent. Right? You need 3 distances, 2 bond angles, and a dihedral angle that collects them. So how many? 1, 2, 3, 4, 5. So you guys start to see as the number of atoms starts to increase, the number of parameters that you need to define the structure starts increasing significantly. So therefore, how does NMR work is that NMR does not look at the structure directly. It looks at the structure indirectly. What do we mean by this? Is that if I can take the entire classroom right now, if I can define distance between each student to each other student, then can I virtually recreate how the students were sitting in my class? So I don't take a picture. NMR is not taking a picture of how the students are sitting. I just ask student 1 to 2, what is the distance between them? I assume student 2 to 1 is also the same distance. So I want to ask you that question. Then I ask student 1, what's the distance between you and student 3, 1 and 3? Okay, so let's say we have 7 students. Let's do this box and finish up. 1, 2, 3, 4, 5, 6, 7. Right? Let's say 1 to 1 is a distance that that doesn't make sense, right? So you realize that anything here is not useful and anything at the bottom is same as the top, because the 1 to 2 distance should be 2 to 1 distance, right? So if I ask student 1 to student 2, what is the distance? Student 1 to 3, what is the distance? 1 to 4, what is the distance? 1 to 5, what is it? 1 to 6, what is the distance? 1 to 7, what is the distance? Let's assume I can measure all. In this case, I can measure all. But in NMR, beyond 5 angstroms, maybe you won't be able to measure. Right? If I end up getting all these measurements, if I put this together, can I recreate how students are sitting? But I cannot exactly say whether you're sitting facing me or not. You could always be at an angle. Therefore, my distance also has to come to get respectively how people sit. Right? And there could be some degeneracy issues here. For instance, if you're having something like this and I'm sitting here, when you end up recreating, you might end up recreating something which is symmetric and opposite also. Okay, but of course, this is not an obvious example. There are other examples where degeneracies would come. So as many distances you collect, you'll be able to define the structure better. True? That's essentially what a NOESY does. In tomorrow's class, I'll give you a little bit of understanding on how these NOESYs are helpful to get distances within a protein's construct. So I'll take some of the examples of what kind of interactions exist between I and I+1, I and I+2, I and I+3, and I and I+4 within alpha helices. And similarly for beta sheets, and therefore, how does the NOESY experiment help? Okay, so this is what we'll finish up with. And I also give some idea, qualitative idea on how chemical shifts could also be useful to understand secondary and tertiary structure of proteins. For the end semester exam, these questions will be qualitative. So please listen to this. If you have doubts, luckily we have enough time to clarify your doubts. Do that before the end sem exam. Thank you very much. See you guys tomorrow.